Now let's look at speeding up and slowing down. Speeding up when the slope of speed is positive, and we're slowing down when the slope of speed is negative. But there's a much easier way to figure out when a particle or when an object is speeding up and when it is slowing down. So let's take a look at a graph. All right, so notice here velocity is positive from 0 to 5. Right? It is above the x-axis. Right? So it's above the x-axis. Right? And if we look in that same location, so we're just going to look from 0 to 5. So notice the velocity is greater than 0. It's above the x-axis. The acceleration, however, is negative. All right? So our acceleration is negative because it is below the x-axis. Right? So we have negative values. So we have positive velocity, negative acceleration. So just think about that for a moment. Let's look at the graph from 5 until, what was that, 5.5 there. All right, so notice here our velocity is now negative. Right? So velocity is less than 0. It's below the x-axis. The acceleration is also less than 0. It's still below the x-axis over here. So over here and here, both spots, it's below the x-axis. So nothing has changed on the acceleration. So notice velocity is negative, acceleration is negative. All right? Now let's look from t equals 5.5 till t equals, what is that, maybe 8.2. All right, so velocity is still negative. It's still below the x-axis. Right? So there's no change here in our velocity. Right? Still below the x-axis. But the acceleration is now positive. So right here at t equals 5.7 or so, 5.6, our velocity, or excuse me, our acceleration changes from negative to positive. So here acceleration is greater than 0. It's above the x-axis. Right? So velocity is negative, acceleration is positive. If we look at the last section of the graph from about 8.2, right, to infinity, notice now that the velocity is positive. It's greater than 0 because it is above the x-axis. Acceleration continues to be positive. It's also above the x-axis. So you might have noticed something here. So velocity is positive, acceleration is negative, we're slowing down. Velocity is negative, acceleration is negative, we're speeding up. Velocity is negative, acceleration is positive, we're slowing down. Velocity is positive, acceleration is positive, we're speeding up. All right, so notice that the two places that the signs were the same for velocity and acceleration, our object is speeding up. So when the acceleration and the velocity, when their signs match, right, then we're going even fast. So here, for the instance of the place where the velocity is negative and acceleration is negative, we're moving in a negative direction ever so much faster. And where the velocity is positive and the acceleration is positive, the object is moving in a positive direction at an increasing rate of change. So if velocity and acceleration have signs that match, the object is speeding up. Notice in the beginning, right, our velocity is positive, the acceleration is negative. Right, so we're moving in a positive direction, but the velocity is negative. Right? So our object is going to be slowing down. Same thing when the velocity is negative but the acceleration is positive. So if the signs are different, the object is slowing down. So we're going to determine where an object is speeding up or slowing down. We're going to find the velocity and the acceleration. We're going to find the x-intercepts, where the velocity or acceleration changes from negative to positive, positive to negative. Right? And use that to determine the intervals where an object is slowing down or speeding up. All right, so let's take a look here. When is S of t speeding up and slowing down? So here we have position, velocity, speed, and acceleration. And we're going to focus on position, velocity, and acceleration. Speed is just kind of along for the ride. Notice it's the same graph as velocity, with the part below the x-axis just reflected above the x-axis. So I broke this down into 4 intervals. Based on what was happening, whether there was a change. Was there a change on the position graph? Was there a change on the velocity graph? Was there a change on the acceleration graph? All right, so we have blue is from 0 to 2 seconds. All right, so if we look at the position graph, notice our position, we have a negative slope on the position graph from 0 to 2. All right, so we're moving in a negative direction. Let's look at velocity. Velocity supports that, because velocity is below the x-axis from 0 to 2. Right, here's, and it's in blue, so right here, right, sort of that change right there. All right, so from 0 to 2, right, our velocity is also negative. And I'm just going to put v of t rather than try to write out velocity. So v of t, is less than 0, it's negative. And actually, next to moving in a negative direction, let's put p of t is less than 0. All right, so the position function has values less than 0. The velocity function is less than 0. And if we look at acceleration, the graph, we are also below the x-axis. So acceleration is also less than 0. The object here is going to be speeding up. And the way we know that is because velocity and acceleration both match. Right? And that's supported by what we see on the position graph. So now let's look at the interval from 2 to 4. We're still moving in a negative direction. Right, because p of t is still less than 0. Right, I shouldn't say p of t is less. P of t has a negative slope. Excuse me. Shouldn't really say p of t as less than 0. We'll just leave that part out. I don't think I can squeeze in p of t has a negative slope. I don't know. Actually, maybe if I get rid of this one. I kind of thought of my wording on that. I'm like, wait, that's not what I meant. All right, if we get rid of this, let's squeeze in there P of t negative slope. Right, because P of t could be positive, it could be above the x-axis. But if the slope is negative, then it's moving in a negative direction. However, when it's moving in a negative direction, v of t will always be less than 0. And in this case, our acceleration happens to match that, which means that the object is speeding up. I'll rewrite it. I can't squeeze it in. There we go. All right, and we know it's speeding up because these two match. There we go. All right. Let's look at 2 to 4 seconds. We still are moving in a negative direction. I'll abbreviate a little bit more. I'm going to run out of space. Again, P of t has a negative slope. If we look at velocity, velocity is still below the x-axis. Right? At 4 seconds, right, it changes from positive to negative, but v of t is still less than 0. Acceleration, on the other hand, which is why I broke this interval up at 2, acceleration is now above the x-axis. So right here, a of t is greater than 0. So our velocity is negative, but the acceleration is positive. All right? Notice they do not match, and that does mean the object is slowing down. And by the way, I think this one might be in your notes. I'm sure, in fact, I'm sure it is. So follow along with me and just fix the part where I had a boo-boo. All right, so right here we have a horizontal tangent. Right, so no change in position at 4 seconds. Right, and we know there's no change because P of t has horizontal tangent. At 4 seconds, notice our velocity changes from negative to positive. So v of t is 0, right? Right here, that's an x-intercept, right? So right there, at t equals 4, the velocity is equal to 0, right? But the acceleration is still positive. I don't think it's on the graph anymore. Oh, it's just that little spot there, right? It's still above the x-axis. Right? So here, what's happening? We're changing position. Excuse me, changing direction. Now, after 4 seconds, right, we can look at whether we're speeding up or slowing down. But right at 4 seconds, at just that moment, there's no change in the position. The velocity is 0, so we can't be speeding up or slowing down. We're just changing directions. And you do have to stop for a moment to change directions. So notice now, from 4 seconds to infinity, our object is moving in a positive direction. And how do we know? Well, we know that because P of t, oh, I should have called it S of t. Simple. See, you call it position function and you use s, I got p in my head. So p of t has a positive slope. If we look at velocity, notice after 4 seconds above the x-axis, that supports us moving in a positive direction. So v of t is greater than 0. And the acceleration remains positive as well. A of t is greater than 0. It's above the x-axis. So the only time that acceleration is below the x-axis is from 0 to 2 seconds. After that, the acceleration is positive. And if velocity and acceleration are both positive, or both negative, our object is speeding up in a positive direction. Right, so in the next Nearpod, I think this is where I was going to stop. In the next Nearpod, you're going to learn how to use, oh wait, I'm sorry, I have one more slide. I just want to go over one more graph, and then I'm going to stop. And then I'll tell you what you're doing in the next Nearpod. So it's important to understand the relationship between a position graph, a velocity graph, and acceleration graph. All right, so this is the position graph. We have distance and time. All right, and notice here, so let's look at the different locations on our graph. And I'm going to graph those as points so you can see what I'm referring to, because I can't point and have you see me. All right, so right here, right, we see we have so our position function has a positive slope. If it has a positive slope, that means that v of t has to be positive. Notice that the slope, so notice that that slope is increasing, right? So that means that velocity is increasing, right? So if that rate of change is increasing, the acceleration is also increasing. This is our object here is speeding up, right? Now if we look at the next location right here, position is still in a positive direction, but there's no change in velocity, right? Notice that our position function sort of looks a bit linear. Let's call it approximately linear. It's not a piecewise function or anything like that, but notice we're approximately linear looking. That would give us a constant rate of change. So if we have a constant rate of change, right, the velocity will still be positive, right, because we're moving in a positive direction. But if there's no change in velocity, it's just staying at that same amount of velocity, right, and staying constant, then acceleration is going to be 0. All right, so there's no change in velocity because velocity is positive and constant. If velocity is constant, acceleration is 0. All right, so if we continue right here, all right, notice that our velocity, so we're still moving in a positive direction, right, which means that velocity is still positive, right? But that rate of change is decreasing, right? So notice that our position function, the slope is getting less steep. That means velocity is decreasing, because velocity is just the slope of the function. And that means that acceleration is going to be negative. Our object is slowing down. And if you think about it, it has to slow down, because right here, velocity is going to be 0. And why is velocity going to be 0? Our object is stopped. And it's stopped because it is turning around. So next, our graph starts to move in a negative direction. Let me go back to my purple. All right, so here, the velocity, so notice the position graph has a negative slope, which means that the velocity is negative and the acceleration is negative, right? Because we were at 0, right? So our rate of change is increasing, which means now both the velocity and acceleration match. The graph is speeding up. Kind of the same as we had over on the other side, right? So once it starts speeding up, the velocity is still negative, right? Because our position is becoming more negative. We turned around, right? We're now moving to the left. And we know that because the position function has a negative slope. So our velocity is going to be negative, but it's at a constant rate, which means the acceleration will be 0 because there's no change in velocity. Right? So here, our acceleration is still negative. Right? We're still, the position is still in a negative direction. The acceleration is positive, right? So we have acceleration that's positive, velocity that's negative, because now there's a change, there's a positive change in our velocity because it's becoming less negative. So if the velocity becomes less negative, right, that's going to be a rate of change. That's going to be a rate of change. Your acceleration is going to change. If it's becoming less negative, your acceleration is positive, and your object is slowing down. And that makes sense because we're going to stop pretty soon. All right, so here, this whole section here, there's no change in position now, right? Because our position function, we'll call it P of t again. P of t here has a constant slope. Excuse me, not a constant slope. Excuse me. Well, it's a constant slope, but the slope is 0. So P of t there has a slope of 0, right? That means your velocity is 0. Your acceleration is 0. And why is that? Because your object is stopped, right? There's no rate of change in the rate of change if the rate of change is 0. And there's no change in velocity if your position isn't changing, right? So here we are comparing position, velocity, and acceleration. In the next Nearpod, we are going to look at all three simultaneously and create a sign chart to figure out when objects are speeding up and slowing down. All right, thanks for watching. Bye for now.